till now for a very amazing conference. Unfortunately, I was traveling the last 2 days, and I just basically started at Illinois Institute of Technology. So the last couple of days I was traveling. Even I was emailing Dr. Ashraf like the translation from the airport, like I put it using my phone. So thank you for the opportunity to be today with amazing scientists and give me the opportunity to let you know more about my current research and my research group at Illinois Institute of Technology. So for people who don't know me, I'm actually graduated in 2005 from Alexandria University. I ranked at the top of the chemistry department, and I hired as a demonstrator or TA, as whatever you want to call it. And then I was a lecturer. So I spent some good time at Alexandria University working with very nice people. I love it, and it was a very good experience. However, I traveled to United States to do my PhD, but originally I'm from Alexandria. If you didn't visit Egypt, I just had this slide. I always have it in my presentation because I'm very proud where I am from, and I always encourage people to visit Egypt. It's an amazing country. Almost people here in the United States think that Egypt is expensive to visit. I always tell them, hey, I was a professor in Egypt and my salary was 5,000 Egyptian pound, which is like $300. So if I can survive with $300 with a family in Egypt, definitely, you're gonna be like, if you go to Egypt, it will be a lot cheaper, and we have an amazing coast like Mediterranean or like the Red Sea. So it's amazing. Actually, people when they go to Hawaii think it's Hawaii or Miami Beach. Believe me, I went to for example, Marsa Matruh, which is close to Alexandria, or our coast in Mediterranean. It's amazing. It's beautiful crystalline water, and there are a lot of amazing places to visit. So don't hesitate if you have any question about places to visit in Egypt, because I explore a lot of area, and unfortunately, a lot of Egyptian people even don't know a lot about the places where to go in Egypt. We have fantastic places where we can go for camping, or because I think it's not part of our culture. People are super busy with the life, but I think part of our life we need to take a break. Anyway, I'm not gonna talk about that, but please, if you have any question, let me know. If you are not from Egypt, if you are from Egypt, most likely you know what I'm talking about. So as I told you, I graduated in 2005. I was hired in the university. I was teaching since then. And then in 2011, I started my PhD. I got a scholarship to join University of South Florida. Actually, I'm proud that I finished my PhD in 3.5 years. So I think I was lucky, and I mean, my hard work paid off, which I believe anyone from Egypt will be also a very hard worker. Or any international student, I would say, they are come for a reason. When they travel for a study, they come to travel to achieve something. They have a goal. Most of the students I met are amazing, but I was working 24/7 in the lab. You can imagine to finish my thesis in 3.5 years with a decent number of publications, around 10 papers. Again, as Dr. Amal said, it's about quality, not about number. I have a good number of JAX paper and Govanta, which has like impact factor. JAX is like 15, and also I had a US patent during my PhD. Then after that, I went back Egypt to resume my position after I get my PhD, or I earned my PhD from USF. And then I secured funding by the first time to have a collaboration with Department of Energy, to my knowledge, between Egypt and United States. So I secured funding by doing collaboration with Pacific Northwest National Laboratory, which is one of the Department of Energy, one of the national labs of Department of Energy at United States. So I came here as a visiting assistant professor to do some research in nuclear waste management. And then after that, I decided to stay, and I moved to National Energy Technology Laboratory to work as a research scientist in carbon capture, as Dr. Amal was talking today about global warming. So this is mainly NETL work. So National Energy Technology Laboratory, this is our work about carbon capture and conversion. Also, I got some scholarship to visit UC Berkeley during my time at NETL. So there is always opportunities. That's why I was asking Dr. Amal if there are some opportunities with UNESCO. You got to explore. I'm giving this advice to the students. You got to look, you got to do your homework and look. I'm sure you will find a lot of opportunities, but unfortunately, most of, I don't want to say that, but most of Arab people or Egyptian or whatever, they used to take the thing by the spoon. A lot of the students reaching out to me asking about GRE, about TOEFL. I'm not sure if this is our fault or our mistake as a teachers or as a professor that we don't educate our students about travel and about requirement of travel, because I received a lot of applications from India, from China, and from like Middle East, not much, which I believe it has to do with the knowledge about travel. So I think part of the UNESCO maybe if there is like some like branches in Africa, as you explained, Dr. Amal, if you can explain to the student, I'm sure maybe you're already doing that, but I think it's important to bring that to the table to tell our students about the travel, about the research opportunities to do PhD or master outside. I know, for example, at the Whale University or private university, because they have money, I'm not sure, they actually tell students what is GRE, what is TOEFL, what are the requirements for travel. But I think this is something important we got to educate our students about in public universities. Okay, I'm not talking about private one. Private one, student go with their money, but I think public universities like Alexandria University or Cairo or other universities, I think they have amazing students as well that you need the right opportunity to be highlighted and push them and show them the right way and where to start. So these are a picture of one of my, this is my actually my last lecture at Egypt in 2005 before I traveled. This is my student at USF. Just I love my students. I love teaching. Actually, my dad is a teacher as well. So now I want to like bring this announcement here. I'm actually currently recruiting new students to join my group for the coming spring at Illinois Institute of Technology. We might have some opening in the future, but I'm talking about the coming spring. If you have, I already have some posts in LinkedIn and Twitter, so please go and check our social media. And if you have any question, please email me. And for postdoctoral positions, we already have some candidates. So for postdoctoral, if you are interested, you can email me. I will keep your file, but we already have some candidates for postdoctoral position. So I'm also a founder of SCEMAT. So this is a company I founded in Pittsburgh. It is like located or used to be located at Pittsburgh. Now we're moving to Illinois apparently because so we've done a lot of work in the past, and we're thinking how we can let me like I don't want to annoy you with this noise. So so we've done a lot of work in material science, nanotechnology, membrane separation, gas storage, gas separation, drug delivery. So I was thinking, can we bring our material to the bench, to the market? That's why this was the motivation, or one of the motivations drive me to open this company. It is now in US. I hope we can have some international network. I already have some international network at Spain, but I hope we can spread it more, and we can be like one team and work together to make materials for because we are working in material science or material chemistry or porous material, membrane. So it's amazing material which actually spread it in all type of fields, medicinal, energy, environmental, and so on. So just for this 2-minute video, I just want to share you some of our published work and the work we've been doing in different institutions, and what we have done over the last couple of years. So I will leave you with this for like another 30 seconds. And please follow our social media and Facebook and LinkedIn and Twitter for future opportunity if you are interested to do PhD here, or if you are interested for position in our company or position as a postdoctoral in my lab. All right. So I would like, before I start my talk, to thank all the collaborators and for their support, because without a good network, without a support from good colleagues and friends, this work that I'm going to present is not going to happen. And I really appreciate all the support I received from my supervisor, from my colleagues and friends. So I'm not sure if I can minimize this or not, but anyway, so my work basically in material engineering or materials chemistry We make porous material, composite, membrane, also solvent, and the hollow fibers or fibers for different applications. So the applications I'm interested to, or I've been working on, including but not limited to separation or gas storage and separation, environmental application, nuclear waste management, sensing, in environmental sustainability, and biomedicine as well, including drug delivery and catalysis. So this is here some of like the work that highlighted recently in the news, you know, for some of our recent work in nuclear waste management and also for carbon capture and conversion by different institutions. So I'm glad and honored and humbled to receive such recognition. So today my talk will be about carbon capture. So I'm not going to talk about other applications. I'm going to focus only because of the limitation of the time about carbon. I'm going to talk only in carbon capture and separation, because it is one of the main problems now. So there is no doubt that carbon dioxide or greenhouse gases, carbon dioxide is one of the greenhouse gases, if you know. But it is a major source of greenhouse effect, but there are other gases actually also causing problems, such as methane and other ones. So today we're going to focus about carbon capture, because the methane problem is not currently going to be happening like maybe in 20 years, but for carbon dioxide apparently is causing what all of the mess that we see from you know, for global warming that affecting the forest, wildfires, including like you know, all this kind of weird weather that we're seeing every day. So I hope as a scientist we are going to contribute solving the problem of carbon dioxide or greenhouse gases in general, to capture and do some aggressive research to do to resolve that problem. So today I'm going to talk about task-specific material for carbon capture, including solid sorbents, advanced composites, multi-component membranes, and finally for 3D printing membranes. So for the solid sorbents, we can capture and just show you, I'm going to show you some of the design strategy that you can include for porous material to capture carbon dioxide. Specifically, we can introduce a binding site. I'm not sure if you can see that because on my end I cannot see it. Binding site, molecular sieving approach. We're going to talk about that, or creating carbon dioxide trap. So the materials I'm gonna, as I told you, I've been working in all type of material, including polymeric material, zeolites, metal organic framework. Today, I'm gonna focus more in metal organic framework. So metal organic framework, or MOFs, is composed of like metal salt, as you might know, reaction with metal salt with organic linker to form a like two-dimensional or three-dimensional structure that characterized by their permanent porosity and in like inherent like modularity. So the modularity of this amazing structure is amazing because you can fine-tune the pore size and the pore chemistry to target a specific application. And if you have a porosity, you can definitely use it for many applications. But today, we're going to talk about only carbon capture or separation. But this structure, you can actually make like infinite number of structure, because it pretty much you can use all type of metal ion in the periodic table with a combination of like organic linker, like with two end or more. Like anything that can donate electron acts as a ligand, and it can form an infinite structure with 2 points at least for connection. You can make them off. So you can see there are many possible, and the sky is the limit. The sky is the limit. Yes, you can still make a new structures. Even there are over 60,000 reported structure for MOF, over 60,000. However, the sky is the limit for your imagination to make a new novel material. So this is here like one of the approaches we use to separate carbon dioxide, because the kinetic diameter, or KD, or kinetic diameter we call it, for carbon dioxide apparently is smaller than nitrogen. So we can, if we can make a materials that the pore size is just above the kinetic diameter of carbon dioxide, then we can do basically separation based on the molecular sieving mechanism. How we can make a material with such a pore size? There is an approach called isoreticular synthesis, which apparently using like an organic linker that can has a short organic linker, so we can have a small pore size like this class of material. So I developed this class of material. Actually, one of my students was like an Egyptian one, who is, his name is Tahir Hussein here. So he was undergraduate student working with me, and he is with me in this publication. So we work by design. We don't just grab metal from the shelf and mix it with organic ligand and hope something will work. As you see, all of this structure, actually, we call it isostructures. This structure has the same topology, same connectivity that because this we call it a platform. So we do stuff by design, so we can control over the pore size because it's self-assembled. It can the structure well organized, or the molecular building unit of the structure will self-assemble to form the extended structure, because we know the chemistry that forms the structure. We know it is like a platform or one of the unique topology or one of the unique network. So we were able to control the pore size. Here, if you are working in storage and you're looking for a high surface area, you can use this one, for example. If you're looking for drug delivery, if you want to like encapsulate some drug, because I know this meeting has to do with more with biomedicine and medicinal chemistry. So basically, you can use MOF definitely for drug delivery and other application for biomedical application. If you know what is the guest molecule you want to encapsulate, we can talk more if you are interested. So we can use other approach by having a template to control over the pore size. Like this example here, I used here a solvent as a template, which kind of one of the first time to use that. That's why we have JAKs, also not because the controlling over the pore size, but also the properties of the material was novel. But this is an example for templation where we can control over the interpenetration or control over the pore size by using the right template, like here, using tertiary butyl formamide versus DMF or dimethyl formamide or ethanol with tertiary butanol. You can see larger guest molecule will afford a larger pore size, for example, for this particular framework. And of course, other guest molecule can be used as well. And after, there are actually many papers in that. We can also introduce some strong functionalities that can strongly interact with the carbon dioxide, like this platform here, like we can see from the isotherm. The steep, the uptake here actually representing the strength of the interaction with carbon dioxide compared to nitrogen and methane. So this material definitely is more selective for CO2 or carbon dioxide compared to nitrogen and methane. This is like one of our US patents. We have a couple of patents submitted actually for other material, but this is one of our early patent in carbon dioxide, making a novel class of material for CO2 capture and separation. And also we can use it for other gases as well. So we can also introduce, I'm not sure if you can read it, but it says here cooperative binding site, where more than one binding site can interact with CO2. We can control even the distance between this binding site by choosing the organic linker, because this material is just only the building unit. This is extended structure, but I'm trying to show you here that we can control even the distance between these two binding sites by playing with the organic linker or the length of the organic linker. Now I'm going to switch the gear and talk about advanced composite and multi-layer membranes. So this here, actually, we can use the existing class of metal organic framework. As I said, there are over 60,000 known structure, which combination to make a composite, you can have like more than 1 billion possibilities. So, but these possibilities, the good about this material or this approach, that these 60,000 structures, they are well defined structures. They are, people already published data about it, and it is defined structure. So it's gonna save you a lot of time to make a new material because you already know the structure, you know the properties. So you can make a composite that carry the best of the properties of this composite. It depends what you are targeting, but definitely this component will not be choosing randomly. It depends on the compatibility between the component and how you're gonna make material with no defects, and depend also what is the properties you are trying to achieve. So this one of the approaches I used, maybe one of the first papers about that kind of work, especially it is maybe the first one where we can have a chemical connection between the different layer of MOFs. So the idea for, or the motivation for that work is, if you are working with a MOF that has a large pore size, if you're doing separation, as I mentioned, using molecular sieving, you will not achieve good selectivity because the larger pore size, everything will go through. As I said, nitrogen is bigger. So if you make a small pore size, you can definitely reject the nitrogen and separate carbon dioxide. But if you're trying to make membrane, people working in membrane will know I'm talking about. You will care about permeability also, not only selectivity. You will have permeability, basically talking about flux or how much gas will go through the membrane. In this case, I know some talk today was talking about water, like liquid separation. In this case, we're talking about gas separation. So we will achieve the high permeability, but we're going to lose the selectivity in case of membrane or sorbent. While if we're trying to use a MOF that has a larger bore size, you will achieve the selectivity. However, the permeability will be very low because of the slow kinetic or the slow diffusion kinetics through the bore size of these narrow bores of the material. In addition, if you're trying to make a material for gas storage, this material will be very poor because of the low surface area, while this material will have a good surface area for the storage. So the question is, can we make a composite that has the flavor of both? And this was the motivation of that work, is to make a selective layer with tiny pore in the surface and coat imagine if this is like inside like a large bag, and this bag has a narrow hole, so only the small molecule can diffuse inside this large bag, so we can achieve the selectivity as well as permeability or the storage capacity if you are talking about solid sorbent. So this is why we use this approach actually for solid sorbents and as well as for membranes. But remember, the interfacial compatibility between this layer has to be fine-tuned, and we got to figure out how we can make a defect-free interface. Because if you have a defects in the interface, then basically the gas can escape in these defects, let's say, or interface defects. So the idea is to make a composite that can rule the all like Lord of the Ring. I'm not sure if anybody is a fan of that movie, but it is a nice movie. It's a lengthy movie, but it is one of the good series of movies that I watched. So here is the thing, I just choose for a proof of concept because as I told you, this is like the first example where we can have a chemical compatibility between the layer of the MOF, even they have different crystal symmetry. So we choose this class of material to be the selective layer, and this class of material, these two examples here, to be these two MOFs with a large pore size to be the high surface area material, the internal layer, while this will be the one in the surface was only 4 angstrom pore size. So again, we care about compatibility between the layers. So we use two different approaches to demonstrate our concept. The first approach, we can basically, this is MOFs, metal organic framework, so it is coordination polymer. And the surface of this MOF will be decorated with organic linker, like in this case, a bipyridine here. So we can, this bipyridine, this crystal structure, actually the one we are going to grow in the surface has the same symmetry, but different pore size or dimension of the crystal. So we can just replace this bipyridine with similar ligand, but shorter one, like the pyrazine. Pyrazine is similar chemistry like the bipyridine, but shorter one, so we can achieve a smaller pore size in the surface. So we do that through layer by layer technique. I think today we heard some talk about layer by layer approach. So we can just graft the surface. In the surface, we can graft the bipyridine. We can monitor that by different approach using IR, for example, as a straightforward one to see if we have pyrazine. Of course, we wash in between to be sure there is nothing extra in the surface or inside the pore of the material. And then we start to add the metal salt to grow the other layer. And we do that layer by layer until we have enough coverage. Remember, we don't need to grow too much of this selective layer. We just need some skinny layer with no defect in the surface, and we can monitor that through testing the performance of the material to see how much performance improve. Also, we can use the SEM, the EDX analysis, and X-ray, BXRD to see the growth or monitor the growth of the material to figure out how many bi-layer or how many layer or how many cycle required to have enough coverage on the surface to have a good performing material. So the other approach is basically using a chemical connection between these two layers by grafting function group in the surface that can interact with the other layer. So we use a MOF that has open metal center, like here we have a MOF that has some coordinated solvent, so we can knock out this solvent and maintain the porosity of the material by just using vacuum and heat. Actually, the change in the color, this is observed color, because when you have a cover, for example, you have cover, you have methanol coordinated or water. Once you activate this cover and remove this, so basically the color of the material will change because it's changing the coordination environment around the metal center. So the color of the material, even without UV spectroscopy, but also by just looking to the material, you can see the effect of removing the solvent. Now the material have actually unsaturated metal center, which is hungry to interact with ligand to fulfill the coordination environment because it has missing the solvent. So now we can put like a grafting group such as the pyrazine, which is our ligand to make the coating of the shell layer. So now we can add the pyrazine in non-coordinating solvent. So now only the pyrazine can coordinate. Again, the color will change again because we have a different coordinating group. It can coordinate with the metal. Also, we monitor that by IR and other techniques to see the growth. And we wash to remove any excess or extra pyrazine, followed by adding the metal and so on until we make a successful growth of the second layer. We use for the first time, this is one of the pattern we are working on, like for the layer by layer technique, this continuous flow technique, where we introduce the metal ion from one side and ligand from the other side, and grow that inorganic membrane in the surface of the alumina disk in the middle. So we monitor the growth, as I said, by many techniques. And for the sake of the time, I'm just going to show you this beautiful SEM and the EDX analysis and the line scan. So we can actually, I intentionally use copper as an inner layer and nickel in the surface, so I can see the growth or monitor the growth using the line scan and EDX analysis to monitor the growth, and we can see how much we have in the surface by EDX analysis. But you can see intentionally for this particular one also I make the H plastic crystal large crystal and the nickel small one, so we can see the beautiful growth of the second layer on the surface of this large cubic octahedral MOF crystal. So here is a performance just to explain to you when we make a composite why the properties will be better than the individual materials. Remember, the idea here is we have a high surface area material, which in this case, this would be this material. This material, high surface area, you can see, again, for people not familiar about gas absorption, this is the relation between uptake and the pressure. So you activate the material, you remove any gas solvent, and then you will start to introduce the gas and see how much gas will be taken at each particular pressure. So if you have a steep uptake, that means this material is hungry for the gas or gonna take the gas aggressively. So that means, for example, here for this particular one in red, you can see a steep uptake at low pressure. That means there is a strong interaction. While this material here in greenish or blue color, it has very poor interaction. However, because this material has a high surface area, so at 1 atmosphere, it has like almost doubles uptake compared with these materials, which is like the shell layer. You can see the shell layer surface area is only 200 meters square per gram. So the uptake was the material basically saturated at 60 cc per gram. So the material saturates very quick. While the other material is not saturated, actually, if you increase the pressure, it's going to take more and more of carbon dioxide because the surface area of this material is almost 10 times the surface area of this material, like around 2,000 meters square per gram. So then we, somebody is knocking the door. I'm not sure, one of my colleagues, but anyway, I'm just going to continue. Okay, see if you knock again. So then this is here the material in the middle. You can see the material in the, let me see who is knocking. I'm going to come back. I'm so sorry, guys. I'm just new in the university, so a lot of students and faculty is not coming.
Hey, good. So one quick thing. So the walls are going to clean.
Oh.
And I'm emitting.
So sorry, I'm also in the conference. So I will. Okay. Sorry, but it's okay. No problem. No problem. I'm so sorry, guys. It looks like because I used to teach a lot of lecture in Egypt, and my voice is kind of loud. So my neighbors have a meeting as well, and it looks like the wall is not very good insulation. So I do apologize for that. I always notice when I give a lecture here in the United States, people saying your voice is loud, and a lot of people using like mic. I mean, okay, thanks to the Egyptian experience, to give me the ability, alhamdulillah, for loud voice. So anyway, so we can see here the material in the middle. It has this is actually the core shell material. It has a steep uptake like the shell layer, and also it has a high uptake like the core layer or the high surface area material. So we can make completely new material by just using the approach of composite materials like I presented. So now I'm going to talk about different type of membranes. This other membrane was inorganic membranes or composite. Now I'm going to talk about like mixed matrix polymeric membranes. And then I'm going to talk to you, letting you know about our recent approach to scale up membranes. So mixed matrix membrane, it is from the name mixed matrix. So you have polymer to give you the processability. You have filler, which is a porous material such as MOF to give you the selectivity. So we can make beautiful membranes that has properties of the polymer with processability and mechanical strength, because MOFs are crystalline material. So if you asked me, is the inorganic membrane you can bend it? Of course not, because this crystalline material is going to break and it will have a problem. So we're going to just present today mixed matrix membrane for carbon dioxide separation. Definitely there are other applications we can use it for. So the idea for mixed matrix membrane for separation, people working in separation are using gases, you know about Robinson upper bound. So basically this here, the data for a polymeric membrane. In the case of membrane, we care about selectivity and permeability. So you looking definitely to achieve high permeability and high selectivity. So this is the target area. So most of the work done so far in mixed matrix membrane, people using two components, which lead to a trade-off between permeability and selectivity, apparently. Because if you use polymer that has high porosity and a MOF that has high surface area to achieve high permeability, you're going to lose the selectivity. While if it's using a dense polymer that has a small pore size, such as these ones, and MOF with a small pore size, in order to achieve high selectivity, you will have a very low permeability. So definitely the optimum one to use polymer with high surface area, MOF with low surface area but small pore limiting diameter or a small pore size to achieve a good membrane. However, there are only handful number of good candidates that show good properties. So definitely a new approach needs to be used to achieve like such high permeability and selectivity. So we can conclude from that the two component system that what people have been using, it definitely is not good enough. So we need to use a new technique. I'm calling it formulation technique or multi-component mixed matrix membrane. This is the first time to use this approach. Formulation definitely used in the drug a lot, but I brought this approach to our group by using the technique of formulation to where you can have two components, three components, or more in order to have a composite that has the properties of this mixture. Again, the material will not be chosen randomly. Every candidate will be chosen based on the compatibility to avoid defects, because you are separating gases. So any minor defect, you're gonna lose the selectivity. And also compatibility between MOF, because an inorganic or metal organic framework, and the polymer. So this is a big problem, because now we are trying to combine crystalline or small crystals with polymer. So definitely you got to have, in this particular example, we have a chemical connection between the MOF crystals and the polymer, but I'm not going to talk about it because of the sake of the time. But we have chosen this MOF carefully to have a chemical compatibility between the MOF and the polymer. So one of the polymer we used has high permeability. This polymer with intrinsic microporosity, and the other polymer has high selectivity, and everything is added by the formulation. So we added gradually each component to monitor the effect of adding its constituent to achieve the target high permeability and high selectivity. Because this, again, done, even if it's engineering, but it is done by engineering design, we were able to remember Robinson upper bound, with the area above the line here. All of the membrane, the 11 membrane we fabricate are actually having an amazing properties in terms of permeability and selectivity above the boundary. This here, like polymer blend, PP is polymer blend, are actually the polymer without the MOF. We can see by adding the MOF or porous material, you actually achieve the selectivity as well as the permeability. You can read more from our publication, and I will be happy to answer any question if you have, or if you have any question, you can send me. So also, because I received this question in my last presentation for another conference, so I decided to put it here, which is the cost analysis. People telling me, okay, what about cost analysis? Were you able to reduce the cost? Yes. So this here is the blend or the polymer. We do cost analysis by collaboration with the computational colleagues, and they done the calculation for the cost. CCC is the cost for carbon capture per dollar per ton of carbon dioxide. So this is the cost of carbon capture per dollar per each ton of carbon dioxide. We were able to reduce the cost from $65 to around $52 by introducing this approach of mixed matrix membrane. So recently, collaboration is important and networking. So I appreciate really the opportunity today, and I'm always open for good conferences, to meet nice people, and open for collaboration, because always nice ideas come from collaboration. This example, for example, here, I met Professor Jeff, he's from University of Connecticut, and Mayor in like the AICHE meeting was its American Chemical Engineering meeting, and he was presenting about 3D printing for polymeric membranes, and I said, okay, can we use this also for mixed matrix membrane? Somehow this work was not published so far, even it looks to me very obvious to make mixed matrix membrane, or TFC in this case, or thin film composite mixed matrix membrane, because we can control by 3D printing the thickness of the membrane to have like a few micron thickness, because thicker the membrane, slower is the diffusion, and lower would be the performance as well. So thinner is better, definitely, if you can make it thinner with no defects. And this was like the first example. We actually was invited to do this submission. I know RSC at anyone of the good journal, but we were invited to this journal. That's why we decided to go. It is still a very good journal. And thanks for the editor for the invitation and for accepting the paper. So this is, as I said, one of the examples showing you that now we can scale up thin film composite membrane, mixed matrix membrane in a large sheet by just using 3D printing. So I'd like at the end to thank all of you, and please, if you have any question, you can email me, or we can now answer it now if you have time. And thank you for again, Dr. Ashraf and the committee for such a nice invitation. And please, if you have any question, let me know. I'm gonna stop sharing. Yeah.
Okay, thank you, Dr. Sameh. So we are, if anybody has any questions for Dr. Sameh, or maybe you all exhausted. Okay, thank you, Dr. Sameh. And now we are happy to announce that we already got to the end of our international conference. I just would like to give you a brief about Bionet 7. So Bionet 7, in brief, that we do have participants from 15 countries, 35 academic institutions, and 5 keynote speakers, 8 plenary and invited speakers, 8 oral presentations, more than 25 posters, and 10 scientific sessions, and 1 poster sessions with winner of Nahla Al-Hasisi. We do have a lot of topics like COVID-19 associated mortality, keratin nanotechnologies, mesenchymal stem cells, dynamic susceptibility of antibiotics, nanoporous materials, drug vehicles, functional porous materials, nanostructures, materials based sensor, immunoposting food during COVID-19 era, potential target of bilitepsin in silico toxicology, antifungal effect of kombucha tea, expression of liver fibrosis, CD44 biomarker, cartilage tissue engineering, endofighting fungi induced Huntington disease. This is some of the topics that has been presented in Bionet 7. Finally, we would like to appreciate our sponsors, the MA Trade Company, International Center of Arbitration located in Cairo, and the Clini-Lab Company. And we would like to express also our appreciation for our partners, Hasheimte University in Jordan, MIU University, Misr International University in Cairo. Finally, I would like to thank everybody who has given his own time, my own team in Bionet 7, speakers, participants, oral presenter, poster presenters, everybody. We thank you very much. Sorry for such very long day, but it was very, very informative. Finally, I would like to see you all in Dubai in 2023. Sorry.